Okay, hi everyone, welcome back to our Calculus 3 class notes. We're still in section 15.4. We're at the bottom of page 95 here. And so 15.4 is looking at how to do double integrals in polar coordinates. And often we want to be able to change some Cartesian integrals into polar coordinates or polar integrals because evaluating this polar integral is actually going to be easier than trying to evaluate the Cartesian integral, which I will show you at some point soon. Okay, so we want to evaluate the double integral over a region R in the xy plane of f of xy dx dy or dy dx, it doesn't matter which. Okay, and I want to change that into a double integral over a region G, where G is the same region as R, it's just described in polar coordinates, of f of, now x, remember, is r cosine theta, so the conversion from x to polar is that x is equal to r cosine theta, and y is equal to r sine theta. And then this dA, dx dy or dy dx, is equal to r dr d theta. Okay, so let's say, for example, we want to evaluate e to the x squared plus y squared dy dx. Now, we could not evaluate this in terms of rectangular coordinates. This is not integrable to us in terms of rectangular coordinates. So changing it to polar coordinates actually makes it pretty easy. And R here is a semicircular region, so the upper half of a circle bounded by the x-axis and the curve y equals 1 minus x squared. So this is the upper half of the circle, x squared plus y squared equals 1. If I put it in terms of y, it's the square root of 1 minus x squared because it's the upper half of the circle. So if I were to put this in rectangular coordinates, the region would be x would vary from minus 1 to 1, and as x is varying from minus 1 to 1 for my outside integral, y is going from the function y equals 0 to the function y equals square root of 1 minus x squared. Again, can't integrate that though. Now I'm going to put it in terms of polar coordinates. So this is a very easy region to describe polar coordinates. It's exactly what polar coordinates are most useful for, is circular or cylindrical type regions. So x squared plus y squared becomes r squared. That's a conversion to polar coordinates for x squared plus y squared. And again, you can see that as x squared is r squared cosine squared theta plus y squared is r squared sine squared theta. So factor out r squared, you get r squared times 1. But that's a very simple, that's the conversion for it. And then dy dx becomes r dr d theta. So then I have to say, well, as theta ranges from, so this is the angle 0, theta ranges from 0 over to pi to cover this region. R is going from 0 to 1 for every single value of theta. Okay, so that's how you get these limits of integration. Now it's an easy thing to integrate. I can do a u substitution. U equals r squared, so du over 2 is r dr. So there's my substitution for r dr. Here's my substitution for r squared. So I get e to the u du. I'm going to pull the 1/2 out in front. You could change the limits of integration here, but I'm going to just remind them, put an r equals, so I remind myself that these are in terms of r. So r equals 0 to r equals 1. Integral of e to the u du is simple. It's just e to the u. Putting u back in, it's e to the r squared. Evaluated from r equals 0 to r equals 1. So that's e to the 1 minus e to the 0, which is 1. So it's e minus 1. And then I'm just left with d theta. The e minus 1 is a constant. Pull it out front, put it over the 2. Integral d theta is just theta evaluated from 0 to pi. So I eventually end up with pi over 2 times e minus 1.